Hi everybody. We're going to be learning about polar and nonpolar molecules here. So if you need practice, you can pause it before I actually explain each one of these scenarios here and bond it, see if you can come up with the combo, the shape, and the ball and stick diagram. I haven't done any of that here for you because I'm just assuming that you knew how to do that. In your note, I also showed you the electronegativity difference. You'll notice here that I did not do that, okay? So in this case, we had a 4-0 combo, and that led us to a tetrahedral shape, and then here's the ball and stick diagram. There's also a polar covalent bond between carbon and chlorine. So technically, there's a little pull towards chlorine. This is a polar covalent bond, and again, there's another pull towards the chlorine. Same thing down here. There's a pull towards chlorine, and there's one here towards chlorine. So there are 4 pulls outward towards each individual chlorine. When you take care of all of that, this molecule ends up being what I call, and I just write down as a short form, non-polar molecule, okay? And there's no net pull. Now, this will be a little difficult to understand because you got to pull up and you don't really have a pull going down. But these 3 pulls, I don't want to be really technical, but on any vector, when you have a pull in that direction, there's an X component and there's a Y component. And so in this case, all 3 of their X components equals going down equals the Y component of these 3 going down equals the Y component of this one going up. And these 3, their X components, just cancel out with each other. It's really hard to visualize. You'll be learning vectors in grade 12 calculus as well, okay? Just picture the shape as it's a tripod, and then here's the neck with the camera up on top. So that's how you would do that one. On the next example, this is carbon dioxide. Now, this is a 2-0 combo and linear. Now, this is a good example to show you how I did multiple bonds. So even though there is a pair of electrons here and a pair of electrons here, a pair there and a pair there, I only consider this one pair and this another pair. Thus, the 2-0 combo and the linear shape. Now, on this example, there is a pull towards the oxygen, and there's another pull towards the oxygen. Now, another thing, I don't suggest you draw these little arrows because they can tend to be confusing. In my mind, I'm just going, okay, there's a pull that way, there's a pull that way. They're in opposite directions, so again, there's not going to be a net pull. The pulls cancel. And because the pulls cancel, this is called a non-polar molecule again. Now, you want to be careful. On a test, on an exam, if I ask you, is the molecule polar or non-polar, I don't want you just writing on the paper non-polar, because really there are 2 non-polars that we can be talking about, right? We can be talking about a non-polar covalent bond or a non-polar molecule. So you really need to specify. And with my short forms, it's really not that big of a deal to just go either NPCB for a non-polar covalent bond or NPM for a non-polar molecule. So that's how that one worked. This is a strange one. When you bond this one, you end up with a 4-0 combo, and you end up with a tetrahedral shape, and here's the ball and stick diagram. Now, there are 2 types of bonds here. Between carbon and hydrogen, these are non-polar covalent bonds. So that means the tug of war between these electrons is tie. So if you were looking at these pair of electrons, you wouldn't see them being pulled one way or the other, so that's why we say there's no pull. So there's no pull here, and there's also no pull here. There is a pull towards the chlorine here, and again, remember, don't really draw the arrows in if you can help it. And then there's also a pull in that direction. Now, hopefully you can see this, that if I have a pull this way and a pull this way, there's going to be a net pull in this direction. Because there's a net pull, we can call this a polar molecule. Okay? This end basically shows this end of the molecule would be the positive end, and then this side of the molecule would be the negative end. Okay, so if you kind of drew what the molecule, what might look like, this end would end up being actually the slightly positive end, and this side would be the slightly negative end because the pull was in that direction. That's kind of what it ends up doing, okay? So that's how you would do that one. Hopefully this is pretty easy to see. Now, someone might be asking, well, Stan, what happens if you didn't put the chlorines here? What happens if you had a chlorine here and a chlorine here? Well, then I'd have a pull, and my net pull would be in this direction. So no matter where you place the chlorines and the hydrogens, you will always end up with a polar molecule. The only difference would be in the direction of your pull. Okay? Here's another example to go through. So this is PCl3, which is phosphorus 3 chloride or phosphorus chloride. It's a 3-1 combo, which is trigonal pyramidal. So it's basically a pyramid with a triangular base. And in this example, there are 3 polar covalent bonds. The phosphorus chlorine bond is a polar covalent bond pulling towards the chlorine. So I have 3 pulls like that. The pulls are not going to cancel each other out. If you remember on the first example, these 3 being pulled apart like a tripod, their x component of the vectors will cancel out, but the y component won't cancel out. You needed this pull going up here to cancel it out. So in this example, there's going to be a net pull in that direction. Because there's a net pull, we call this a polar molecule again. And you'll notice I'm drawing the arrow right through it. I can do that because I'm using a different color, and my diagrams are pretty big. If not, you could always just draw the arrow to the side, and it still gives the same idea. So this side of the molecule would be slightly negative, and this side of the molecule would be slightly positive. Okay? Last example here, this is sulfur 6 fluoride, or sulfuric fluoride. It's a 6-0 combo, so this is an octahedral shape. Now, to picture this, you have basically a straight line right through the sulfur vertically. I have a straight line through the sulfur going this way, going out of the page and going back in, and another straight line. So this here forms an X, and then this is a vertical line straight up, okay? That's gonna help me when I visualize that, when I try and consider, do the pulls cancel? So again, every one of these is a polar covalent bond. So everyone is pulling towards the fluorine. Now, when I'm considering this, the up pull and the down pull are going to cancel themselves out. This pull and this pull are going to cancel each other out. Remember, this is a straight line here. And then this pull and this pull are also going to cancel each other out because that's a straight line. So what happens here is there's no net pull. And even though there's no net pull, this is a non-polar molecule. Now there are small individual pulls, but when you look at the big picture of this entire molecule, that entire molecule would not have a dipole, and you would just consider it a non-polar molecule. So hopefully that helps you in kind of visualizing this, okay? It's very difficult to do. Like I said, you have to visualize what these shapes look like. If you don't do that, then what I would do is at the very end of the note, I kind of gave you a reference guide with 3 kind of easy steps, and I would just go with that. And most of the time, you're going to get it right with that. Okay? Take care. Bye-bye.